We welcome everyone from the Institute Colloquium Committee for the first colloquium of this calendar year. I invite Professor Dipendra Prasad to introduce the speaker.
Hello, welcome everyone. I am very pleased to say a few words of introduction for my good friend Chandrashekar Khare, whom I have known for many decades. In fact, he was a graduate student at Caltech in early 90s when I met him for the first time, and I have been in touch with him ever since. Um, so, Chandrasekhar Khare, as you all know, no, not this title, but he has he is most famous for having proved what is called the Sayre's conjecture, uh, a conjecture which was known to imply Fermat's last theorem, and therefore, for somebody to have the audacity to prove Sayre's conjecture is something mind-boggling. In fact, when I was doing my graduate studies at Harvard in the late 80s and in early 90s, I knew that Sayre's conjecture was one of the most outstanding problems in modern number theory. So it is an amazing feat that Chandrasekhar Khare achieved in the beginning of 2000. He wrote one paper in 2005 or 6, which kind of started the ball rolling, and then he, together with his collaborator Jean-Pierre Vantin-Bergier, completed the proof in 2009. So I feel that Sayre's conjecture has been one of the most outstanding problems in number theory of last several decades, for which he duly gets the credit, and it makes him one of the most distinguished number theorists in the world. And it is an honor we all Indians can feel very proud of. In recognition of his work, he has got many prizes and awards such as the Fermat Prize, the Cole Prize, and the Fellowship of the Royal Society. And presently, he is a professor at UCLA. So, Professor Chandrasekhar.
Thanks, Deependra, for kind words, and thank you for the organizers of the colloquium for inviting me, and thanks for everyone for coming. So I have my voice. I must apologize for my voice is a little bit kind of hoarse. I've been maybe talking too much. So, but I have slides to back me up at this point. So I mean, this book, sorry, this lecture. This lecture is partly a compliment. I mean, I had a reading in the math department about this book I wrote. It's like a popular, it's a mathematical memoir of my journey to the proof of Sayre's conjecture. And this is somehow going to expand. Because the mathematics in that book is at a very impressionistic level. This will also be impressionistic, but it will be a little less impressionistic. I shall try to flesh out a little more some of the mathematics of this book and give you a sense of what is Sayre's conjecture. So I should say, Deependra gave me this kind of introduction. He played a vital role in my career because when I was in the doldrums as a grad student in Caltech, I think in 94, 1994, Deependra was one of the first true real mathematician kind of who met me and expressed optimism that maybe I'll do something in my career as a mathematician. So that was very important for me and was a kind of turning point, I feel, in my. It's very nice to have him in the audience. Okay, so this is going to be. What should I use this or should I just use this? Oh, because okay, I'll put it here. It's better if I'm going too fast or please interrupt me. Okay, so this book, as I said, is an expansion, a little bit of unlocking of the mathematical concepts in this book, and in some ways it is a tale of two symmetries. It's that those symmetries are labeled by the names of two very famous mathematicians who, unfortunately, had very tragic and short lives. They was tragically short their life. Galois, the French mathematician Évariste Galois, who 19th century died roughly at the age of 20 or 21. and Ramanujan, kind of who died at the age of 22. And some of the two objects in this book are labeled, are named after them. So the mathematical tale. So this book is a personal story. It's a story of the mathematician's life. It happens to be me, and it is the journey to this proof of this conjecture. But the mathematical protagonists are these two are labeled by the names of these two very famous French and Indian mathematicians, 1 century apart. And so these objects are called Galois symmetries and Ramanujan symmetries. So I want to kind of tell you what these symmetries are. Right? Just tell you to some extent what these symmetries are. Within this book, I just leave it by labeling them and not really telling you what they are. Here I want to dive a little more into their nature. Okay, so here is a picture of Galois. A very stormy life, stormy and brief life. Died when he was 21. And changed, revolutionized mathematics, pure mathematics by the discovery of the idea of symmetries of solutions of polynomial equations. There's an entire field called Galois theory, and at a more technical level, what I call Galois symmetries are called Galois representations. Symmetries is a friendly name, which is what I use in the book. And this is what this Ramanujan. The Ramanujan symmetries technically in the literature are called modular forms. Initially, in fact, I called them modular symmetries, but then a colleague of mine, Brian Conrad, suggested that I call them Ramanujan symmetries because both symmetries are named after people who have significant connections with these. Okay, so as I said, I wrote this book out of some desire to convey to a general audience the nature of the mathematical enterprise. And so the book is a quest narrative, like the Arthur, like you kind of go in the search for something and describe all your adventures, trying to find the Holy Grail or whatever. So in this case, the Holy Grail is sales conjecture. And it ends with me and Jean-Pierre Mathematical and me proving this conjecture in 2009. I started working on it when I joined Tata Institute as a young mathematician fresh out of a PhD in 1995. So in some ways, it was more than a decade-long journey. And the book kind of tries to illustrate sort of the marathon aspect of mathematical research and the fact that many things need to happen and you need to get lucky. You need to use the ideas of many other people in order to succeed in what you're doing, and you need to persist, and you need to have a strong interest. It keeps you motivated. Rest of this is the story of the book, 1995 to 2009. Though I started much earlier, I was studying in the math audience. I started at the age of 5, but the book is, in terms of the biographical element, it is from when I was 5 to when I was 40. Now I'm much older. I'm writing this book in retrospect, but. So the rough nature of Sayre's conjecture is that Galois symmetries are Ramanujan symmetries. Right? So these are two symmetries which have a totally different flavor. Galois symmetries are somehow more come from the field of algebra. Ramanujan symmetries or modular forms, at first glance, they belong to the world of complex analysis, calculus. And so somehow the miracle of the conjecture is that you're seeing that these two completely different objects are actually have the same DNA, or somewhat one and the same, or at least very intimately tied together. Right, so somehow it is this. Okay, so maybe I'll brief apology. I'm talking about mathematics, which is like more than 20 years old or 50, 20 years old. But Sayre's conjecture remains a central object in number theory. Although his conjecture has been generalized to other general forms of conjecture. It's still kind of actively pursued by people. But in spite of all the efforts people are making the world over, the original form of Sayre's conjecture is the only form which has been proven. Right, so somehow to generalize the proof to prove these more general conjectures is turning out to be quite a task. That inevitably it will be proven sometime. But so somehow I want to emphasize that this mathematics is still very much alive and kicking. So that's right. Okay. So I'm going to have I'm going to first introduce you to Ramanujan symmetry, the Galois symmetry, and this is going to be like a musical love story. These start lives very apart, and then they come together and meet in Sayre's conjecture. To prove that they are one and the same, then kind of they fulfill their destiny or they wedded together. Okay, so that's going to be the general thoughts. I'm going to introduce you to Ramanujan symmetries, tell you about Galois symmetries, and then so the entire story in some ways starts with Ramanujan's prophetic paper in 1960. So he wrote this paper in which he kind of was doing something that might almost seem random, but somehow guided by strong intuition, somehow he was really getting at something which turned out to be vital and important for mathematics. Right, so he wrote a paper. In fact, this is the only paper of Ramanujan I know. It's in the 1960 paper, and because the kind of math I do is not really directly related to what Ramanujan does. But this one paper had a tremendous influence on mathematics throughout the 20th century. So I wanted to somehow talk about Ramanujan's paper and its great influence on things which happened, and which led to, in some ways, Sayre's conjecture, led to Wiles' work on Fermat's theorem, proved in 1984, and it also played a role in our concept. Okay, so this is the paper. It's called some arithmetical function, and what he's actually investigating seems almost like a random problem. I mean, he's convolving some elementary arithmetic functions and trying to find some estimates, and these things which turn out to be the central things which he studied. One of the things he studied in the paper, the values of the Ramanujan tau function, are error terms which show up in what he's trying to estimate. Right? So some of this is mathematics of error terms, but the error terms took center stage, and they kind of played a big role. His observations about them really played a big role in modern number. So this is what I said. The conjecture Sayre made in the 70s and 80s kind of is in direct line with these observations of Ramanujan. But somehow there was an air of uncanny, right? About Ramanujan's mathematics, there's always the air of uncanny. Someone doesn't know where it comes from. So in some ways, intrigued by what Ramanujan pointed out, well, he was also a kind of phenomenologist, discovered phenomena in some ways, and he also gave some proofs. But there were many things he didn't prove with him. And so somehow people try to understand what he was doing, what is the context, why was he looking at this, or why is it interesting. So somehow it intrigued people like Sayre and Sunit and Dyer and various other people. And that led to a lot of beautiful mathematics, and it also led to conjectures. Okay. So the way Ramanujan, the thing Ramanujan studies is defined by this infinite product. Right? You see it. And so somehow you look at this infinite product of x into x minus 1 minus x squared and complete power, and you just record the coefficients. Right? Those coefficients are called tau n, and they're called the Ramanujan tau function in this order. Right? Somehow you're not the first person to look at tau. Somehow this kind of function was present in the 19th century as well. But because Ramanujan studied it deeply and made these very interesting observations about them, in his honor now it's called the Ramanujan tau function. Right? So somehow for him actually it was more or less a combinatorial object because this product. It's not clear whether he even knew what a modular form was, I'm not sure. But he kind of looked at it. He studied this thing and made a deep and fantastic observation. So in Ramanujan's paper, you will find its first 30 values of tau in this table number. And based on these 30 values, maybe he must have completed more on some scratch paper. He made these really astonishing conjectures, right? With somehow you require tremendous intuition just to look at some values and find patterns. And he was like really had some uncanny sense of finding patterns in data. It's not able to celebrate things. Machine sometimes. But again, Ramanujan kind of has this ability of finding data patterns. So, for example, one of the things he was interested in is how fast this tau will grow. And because these are kind of error terms in some estimate he was making, he wanted to show that they don't grow too fast. And so some of the conjectures were about the nature of the asymptotics of tau. Yeah, then there was some other conjectures. So, but he made these conjectures based on these values. And as I said, it's really a seminal paper because it really set off people on a long journey. Now, actually, rather than thinking of this as a combinatorial from generating function, one should really think of this fx, which I wrote down here, as a kind of more structural object. It's called a modular form. Right? Because somehow that gives more structure to understand Ramanujan's observation. That's what we are going to do. We are going to start with talking about modular forms, which is what Ramanujan's symmetries are twisted or dubbed in. Modular forms are called Ramanujan's symmetries. Right, so what are these modular forms? I'm going to dive into some actual mathematics. Right, modular forms are just holomorphic functions, complex analytic functions, on the Poincare upper half plane. So just look at the complex plane and cut it in half and look at imaginary part of z bigger than 0. And look at functions on the upper half plane. Right? And you look at functions with symmetry. There are two kinds of symmetry here. One is just simple translational symmetry, z goes to z plus 1. So the function should remain invariant when you apply translation. And the other kind of symmetry is a more kind of subtle symmetry, which is how it behaves under Mobius inversion. Where you have this Mobius inversion which sends z to minus 1 upon z, and the modular form of weight k at level 1, which is to say for this full modular group Sn to z, which is the 2 by 2 matrices over the integer with determinant 1. This symmetry is subtle, right, which kind of gives modular forms all its flavor and complexity. So f of minus 1 upon z is z to the k we call the weight f of z. Right, so it turns out that this function Ramanujan wrote down, if you substitute x, so if you substitute for x e raised power of 2 pi I z, you get a modular form of weight 12 and level 1. So somehow that's the connection with these more sort of systematic and well studied kind of things which have been around since the 19th century. Symmetries, focus inversion is a reflection of the unit circle. In z goes to z plus 1 is the translation. I'm going to go to this. Okay, so the modular form, in fact, because these two symmetries kind of together generate a much larger group of symmetries, that can basically SL to Z, we have this functional equation infinitely sort of symmetry under the group SL to Z. And within the space, right, so somehow, I mean, those of you who are seeing this for the first time, it might be a bit tricky to absorb all the nuances of the definition. What you can think of, these are just functions on the upper half plane with symmetry. Symmetry is the entire group of 2 by 2 matrices over the integers. For example, in this book, which is here, I do not mention matrices at all, right? Because in some ways it's not going to be for people who have any awareness of matrices. So some of you don't really need to, but in this audience I can talk about matrices. So these are functions which have some symmetry under 2 by 2 matrices and integer coefficients. Now within the space of modular forms, you can look at those which vanish at infinity. So because they have a symmetry under z goes to z plus 1, you have like you have a Fourier expansion. It starts from A0, the constant term, and then you can look at the subspace of cusp forms for which the constant term is 0. So that's typically a codimension 1 subspace. And these are the gadgets you want to consider. These are what modular symmetry is. As you see, they are kind of belonging a priori to the world of complex analysis, holomorphic function. Okay, so in some way they are kind of generalizations of the cos and sine function and the exponential function. You just have this basic symmetry of z goes to z plus 1. These functions have this additional, somewhat much more involved symmetry. So this is what a modular form of level 1 and weight k is. Right, all you have to think about is the functions of analysis. And now the question is, if you define an object, you first of all have to kind of see that it's a non-empty definition. You need to write down modular forms. So there are some kind of simple modular forms you can write down because the SL to Z symmetry. You can make functions which have this behavior by some averaging process. And these are the so-called Eisenstein series of weight k, which exist as soon as k is an even integer, bigger than equal to 4. And okay, so these are, I'm writing down the Fourier series, the Q expansion of this weight k Eisenstein series, where Q is the variable e raised power of 2 pi I z. And so somehow their non-constant terms, sigma k minus 1 n, are rather elementary functions. They're the sums of divisors of n to the k minus first part. Right? Rather easy to define. The constant term is a bit more tricky and important because it is related to the values of the Riemann zeta function. So the constant term is very interesting. Some of people play around with the fact that this constant term is interesting. Well, the non-constant coefficients are very easy to understand. Okay, so this is an example of a modular form of weight k and level 1, but it's not a cusp form because the constant term is some number which is non-zero. Any questions? Please stop me. Okay, so you can kind of decompose the space of modular form as the space spanned by the Eisenstein series, the one-dimensional space, and its complement to the space of cusp form. So the space of cusp form is defined by vanishing at infinity or constant term being 0. Okay, now the delta function is the first cusp form you encounter in your life, right? So somehow it is the cusp form of the smallest weight, 12. Below 12, there is no cusp form of level 1. So delta function is this function. So the delta function is this fx evaluated at x equal to q. E raised power of 2 pi x. That's why I'll come to it. So it is the first cusp form you encounter, and anytime the first instance of something is always very interesting. So it is indeed a very interesting function. And Ramanujan made a remarkable observation about the delta function and its Fourier expansion, which has tau n, which has this coefficient tau. Okay, these space of cusp forms are very well studied. There's a dimension formula, but there's still lots of mysteries lurking about them. Some of mathematics. So the delta function is this function which we wrote down to begin with. Ramanujan studied it for his own purposes. It's not clear. In some way, the problem he studied maybe has fallen by the wayside, but the function he studied to study the problem, which is the tau function, is made essential. Right? Or maybe it's not fallen by the wayside, but since that's something I don't think. Okay. So the delta function was, first of all, also this delta function was not something new. It was when we studied by Jacobi and various mathematicians in the 19th century. Somehow Ramanujan and a small arithmetic study of the Fourier coefficients of them. We made these remarkable observations. Because there is something again uncanny. When you look at complex analytic functions, you look at the Fourier coefficients, and then you're going to make all kinds of arithmetic observations on them. Some you're mixing categories almost. That's Ramanujan kind of unbounded imagination. You went to places that people would probably not go. Okay. Right, so Ramanujan made three conjectures, or two conjectures. He conjectured the following. He conjectured that tau is multiplicative. The tau of mn is equal to tau m times tau n, right? And this more complicated recursive formula for what happens when tau is evaluated at prime powers. Right? So he made these conjectures just looking at the values of tau n. And then he made this, so that's the multiplicative properties of tau. And then he made this property conjecture about the size of tau. The tau p is at most 2 to the p to the 5.5. Roughly it's of the order p to the 5.5. Now it's very easy to prove that. It's not so hard to prove that it's order p to the 6. Right? So somehow that's a very easy argument. Trivial bound kind of what it's called. But to go from 6 to 5.5 to this power saving of 0.5 took 60 years. Right, and when he had made the conjecture, because again, many of his colleagues did not appreciate why this conjecture is interesting to think about. It was not clear, right, somehow why this conjecture is significant, but it turned out to be. And in fact, one of the central conjectures of this theory of Ramanujan symmetry of automorphic forms, what is called a generalized Ramanujan conjecture. Right, so now this conjecture, the first of this type of conjecture which we made with last So he made these three conjectures, right? Very easy to understand. I mean, in some ways, look at this combinatorial object. Ramanujan just looked at it and we made these conjectures about the properties, right? Under multiplication and in terms of size, order of groups. Alright, so in some ways, the first two conjectures, the properties of the multiplicative functions are part of tau. They can be encapsulated by saying that if you look at this kind of L function, you look at this formal series tau n about n to the s, then somehow it has a factorization, prime measure. Right, so this is the first example in the literature in the world in mathematics of a degree 2L function. So in some ways, what had been studied in the 19th century was function like the zeta function, some way prime counting, which was studied by Euler and Riemann most deeply. And then somehow it has a degree 1 flavor, which is to say if you put x equal to p to the minus x, then somehow the Euler factors are of degree 1. So in Ramanujan's case, he is conjecturing that this L function coming from his tau function has degree 2. Where if you put p to the minus x to x, then somehow the factor at p has degree 2. First time degree 2 Euler factor appears in the literature. And then after that, nowadays consider Euler factor as arbitrary. Any questions? Okay. Am I going too fast? Okay, so now Ramanujan, the first two of his conjectures was proven almost immediately after Ramanujan made the conjecture. So then Mordell in Cambridge, he kind of realized that you can somehow think, rather than thinking of these tau as numbers, somehow you have to endow them with meaning, and then it becomes easier to prove such conjectures. So what he realized, what he defined is, he defined operators on this index by n, the Tn, on these spaces of modular forms and Gus forms. And these operators somehow, I'm not going to tell you what they are, they have some meaning, they have some moduli anything, or they have some meaning in terms of what the modular form the functions of. And because of that, you can prove for these operators the relations Ramanujan had conjectured for his tau. Right? So somehow Mordell thought about the problem more abstractly and kind of defined a series of operators and the connection with Ramanujan tau. I'll give you in a second. And the operators, because they had some structural meaning, he could rather easily prove the relations for the operators which Ramanujan had conjectured for his tau function. So tau Tm is equal to Tm times Tn and the co-prime, and this recursive formula for T of P to the prime parts. Right? And now what is the connection with Ramanujan delta function, or tau function, is that it turns out that the delta function, okay, so for example, if you look at now eigenforms for these operators, right? And if you normalize the Gus forms, which are eigenforms in a certain way, so that the first Fourier coefficient is non-zero, it's always non-zero, so you normalize it so that it's 1, then there's an intimate connection between the eigenvalues of these operators on an eigenfunction, which is the modular form or Gus form, and its Fourier coefficient. So the nth operator acts by eigenvalue, the nth Fourier coefficient. Alright? So then somehow that I'm giving you the proof of the Ramanujan conjecture is that basically at delta is turns out that these operators are diagonalizable, When for the case of weight 12 in level 1, there's only one transform, and it has no other choice in being an eigenform. It is an eigenform. And the eigenvalues of these operators acting on delta are exactly as I said, the Fourier coefficients of delta with the tau. Right? So, and because these operators satisfy the relations you want to prove for the eigenvalues, you derive what you need to know for the eigenvalues. Right? So, therefore, models, so this is what one can we call categorification. You're given a sequence of numbers tau in, and you want to prove something about them, you have to endow them with structure, you realize them as eigenvalues of some Provision operator or something, and then prove relations for the operators, and then as a consequence, deduce the same thing for the eigenvalue. Right? So this is the standard move in mathematics. First of all, you recognize delta as something which has no structure, it's a cusp form. Then you realize that you think of the cusp form and define operators of them, and these tau in turn out to be the eigenvalues. The operators have structural meaning, so that you can prove relations about them which are not visible purely at the level of number. So clearly, it's not so easy to prove properties of tau, right? The Ramanujan conjecture them, he was a great mathematician, he couldn't prove it. So you really you needed to have an idea. The idea was to realize them as eigenvalues of operators. You're just working with numbers and generating functions and so on. You can't mess around with that, right? You really have to introduce some structure and model with that. Okay? So you realize them as eigenvalues of the nth Hecke operator. The Hecke operator satisfies the relation from the conjecture, and the consequence, you introduce the same relations. Right? So if there's one thing to take away from this thing is that the model kind of that Ramanujan couldn't prove it within a year. It was proved by thinking a little more abstractly and introducing some very important operators, which are now extremely important in modern point. Yeah. Any questions? Okay, so now let me give you this quote by this very significant German mathematician Martin Eichler. That there are five fundamental operations in mathematics: addition, subtraction, multiplication, division, and modular form. Right, which is just to point out that modular forms are extremely kind of important and they are fundamental and they're ubiquitous. And somehow they're like almost like an enhancement of basic structure. Okay, now though this conjecture Ramanujan will not get direct to what we will talk about. This kind of estimate on the size of tau p took much longer to prove. Model proved the other two conjectures within a year. It took 6 decades to prove this Ramanujan found tau p is the absolute value of tau p is less than equal to 2 times p to the 5.5. And again, one couldn't just prove it by messing around, right? People could prove things gradually more and more, or but to actually prove it, you really have to give the tau and get more higher meaning. Right? First of all, model gave them meaning as eigenvalues of Hecke operators. To prove this hard conjecture of Ramanujan, it turned out very hard. Of course, one doesn't know whether it makes the conjecture how hard it is. It could be that it was not so hard, but it was hard. It took 6 decades to prove it. It led to at least the way it was first proved, and Colloquium in school had to develop the entire machinery of modern algebraic geometry, and then Delhi was a part of that school, managed to prove it using all of those very modern, fancy tools of 20th century. Right, so it took a lot of work and a lot of development of infrastructure to prove this conjecture. But it was proved, and somehow the way it was proved was by relating Ramanujan symmetries to what I'm now going to call Galois symmetry. Right, so again, somehow you have to interpret the numbers tau p as traces of representation, Galois representation, or what I'm going to call Galois symmetry. Somehow again endow them with some higher order catch-all. That was again the step. And again, as I said, when Ramanujan, people were sympathetic, good friends of Ramanujan, it's not clear. It was not clear when he made this conjecture what was the significance. Right? So Hardy expressed some skepticism, as you know, in the movie, studying Ramanujan, kind of work closely together, we know this, right? That's one must be. But even Hardy kind of course, had great respect for Ramanujan, and he said that I don't see what the point is, but maybe there is a point. So that is all right. So okay, the other thing which actually plays a role in Sayre's conjecture more directly is this remarkable congruency observed. Again, It's kind of crazy to look at congruences for Fourier coefficient of complex analytic functions, right? But Raman did it. So you observed that tau n, which is a very complicated function, there's no closed formula for tau n. So you're going to write down some closed formula. But on the other end, mod 691, when you look at remainders, of course, you're weakening the property of that number. When you look at mod 691, tau n becomes an elementary arithmetic function. It's equal to the sums of divisors of n to the 11th power level. So, for example, tau p is congruent to 1 plus p to the 11 mod 691 for price. So somehow tau n, which is very complicated, becomes very simple mod 691. Now again, this observation of Raman, which he actually proved in that paper, 1916, has proved to be a fundamental significance. Affected kind of cyclotron field and a lot of cells and for example, linear coordination of this. So to the public code. Anyway, cell, like he uses JP cell 691 and gmail.com. So somehow 691 is our favorite number of number theorists. It has this Goldilocks property, it's not too big, not too large, it's not too small, it's not too big, it sticks in the middle. Right, because Ramanujan also, or Ramanujan and his people who came after him, also observed similar congruences for the prime 2, 3, 5, 7, 23 and 691. Those are the so-called exceptional primes. But 691 was the largest and the most common. And a lot of Sayre's work, Sayre and Sesonetta undertook in the 1960s to understand what is the meaning of these congruences. Why do they exist? Why do they exist mod 691 and these other few primes? Why are there no other congruences modular other primes? And using Galois symmetry, they understood all this. Right? So this is the work of Sayre and Sesonetta and Dyer. British mathematician. The significance of 691 is basically that it divides it is the numerator of the 12th Eisenstein series. Okay, I'm not going to tell you this, but basically that mod 691, this Eisenstein series looks like a cusp form. There's a unique cusp form of weight 12, which is delta, which if you can ponder this for days, you can see why this implies. But Ramanujan proved it by hand. He proved this problem. Yeah. So somehow understanding these congruences, it intrigued people, and it played a big role in number theory. As I said, it has a direct link to Sayre's conjecture. Why does this work? Okay, and the explanation for much of what Ramanujan did, or conjecture, lies in Galois symmetry. Right, so Ramanujan, really, I don't think he thought about Galois very much. I don't know if he knew it. But the solution to his conundrum, his questions, turned out to be lie in the realm of algebra or Galois or algebraic geometry. So that's my next act 2. Act 1 is over now. So any questions about Ramanujan symmetries? Yeah.
What is special about 12?
12, I mean, just because that this tau n showed up in the error estimates he was making. And so there's some of the error estimates he was making makes sense for all ways. But weight 12 was the first instance where it was kind of mysterious, where the error doesn't make sense. So in some ways, it's the first time you get a cusp form. That's an interesting point because somehow it's a degree 2 L function. So right, it's L delta S. So if you factor the Euler factor 1 minus tau p to the x plus p to the 11 times x squared, we can go back. That 2 comes from that. The fact that it's a degree 2 L function. Some ways Sayre has told me, for example, that Ramanujan knew that this was some modular form because he knew there was something degree 2 about it. There was some Euler factor can be factored into 2 linear factors. Yeah. Yeah, I think you're right. I'm not an expert at all. As I said, this is one paper I watched. But yeah, I think he did. Yeah, he did work with elliptic functions and this and that, but I'm not sure if he formally knew the definition of a modular form. So I have said that also. Right? He said, yeah. Sayre said that Ramanujan didn't need to know. He knew enough to. So in some ways it's not clear what Ramanujan was thinking, right? Because there was something, as I said, uncanny and untamed. Okay, so let me introduce you to Galois symmetries. So the plot I'm going to tell you about this period in 1973 to 1987. So over a long period, Sayre kind of kept refining his conjectures. I mean, not all the time, it's not probably this, but he refined his conjecture under the stimulus of the fact that this kind of mathematics connection between Galois symmetry and Ramanujan symmetry, someone observed, a French, German mathematician, Khare, observed that this has something to do with Fermat cluster. And if you can prove such things, you will get a proof of Fermat cluster. For the first time, it turned out someone gave a plausible reason why Fermat should be right? Because otherwise, Fermat's last time was some random question, it could be true or not. This time it was implied by some systematic conjecture, and then which led to its why this work on it. Okay, so Galois symmetries, again I'm not going to formally define them. I'm going to give you the most simple example. Right? Galois symmetries occur when you're thinking of symmetries of roots of polynomial equations, let's say defined as rational. Right, look at some. So let's look at the simplest equation. Now, if you look at degree 1 equation, there's not much to it. There's not much to do. They always have rational roots. But for example, if you look at x squared minus 5, right, look at its two roots, it's a complex number. Root 5 minus root 5. In this case, the Galois symmetry, there are two Galois symmetries. One is the lazy symmetry, which does nothing, identity. And the other symmetry is one which switches them. Right? So there are two symmetries. And okay, now what could be similar? But somehow, if you start looking at this as Gauss and so on, there, maybe Euler and Legendre and so on, the 18th century, people kind of discovered great mysteries lurking even within these simple equations and their symmetries. Right? Of course, Galois came later. But yeah, so let me just introduce Galois symmetries and this very simple equation, which is what I do in this book as well. But without going, I'll go into slightly more detail. Okay, so what is interesting about these Galois symmetries is that you can actually attach to a. So these symmetries are basically can be labeled by 1 and minus 1. Right? Basically, 1 is just multiply everything by 1, which does nothing, and multiplying by minus 1, which is root 5 and minus 1. So these symmetries are labeled by 1 and minus 1. So now the question is, somehow, so this is a sign. And now with respect to this equation for each prime q, I want to attach a sign. So either 1 or minus 1. Right, and somehow, so these are going to be called local Galois symmetries. The global Galois symmetries are just 1 and minus 1, but now for each prime, I want to give it a sign, 1 or minus 1. And how is it going to arise? What I'm going to do? Now, this is a bit, I don't, this audience, I would think, probably people have encountered modular arithmetic. Is that right? Mod P, mod N. Yeah, okay. So, that's actually one kind of mathematical, not prerequisite, but it really helps if you know that to read my book. Okay, because if you know that, then you will understand. But okay, so now what you do is you look at x squared minus 5 equal to 0. It has two roots, root 5 and minus root 5. And now ask how many roots it has mod q. Right? So ask whether 5 is a square mod q. Or it's not a square mod q. Right? And so if it is a square mod q, you're going to give it the sign 1. If it is not a square mod q, you're going to give it the sign minus 1. Right? So another way of doing this is look at the equation x squared minus 5 equal to 0. Look at its solutions, mod q. And so the solution, typically there will be either 0 solutions, in which case root 5 is not, does not exist over that field inside mod q. Or it has two roots, right? It splits into two factors. Does that make sense? Right? So it will have either 0 or 2 roots, typically. And then the symmetry is just gotten by looking at the number of roots and minusing 1. When 0 you go to minus 1. It's 2 equals to 1. Right? So basically, you attach a sign to a prime via this equation. Give it the sign 1 if it is if q is a square mod p. Q is a square mod, either 5 is a square mod q, and give it the sign minus 1 if 5 is not a square mod. Right? So anyway, so some simple-minded operation. Basically, this point counting solutions of polynomial equation over modulo practice. Okay, so as a concrete example, if you look at q equal to 13, the equation x squared minus 5 equal to 0 has no roots. Not 13, you can check. You can just plug in 0 up to 12 and see if you get something different by 13. Therefore, the number solution is 0. So therefore, the sign you attach, the local Galois symmetry at 13 is minus 1 with respect to this equation. And if you look at q equal to 19, then if you look at 9 squared and minus 9 squared, you get 81. Right? It leaves a remainder of 5 and divided by 19. Right? And therefore, it has two solutions. And therefore, you give it a sign 1. Right? So, given I'm just attaching. You just attach a sign to each prime, depending on whether 5 is a square mod that prime or not. Okay, now this looks like a very random. This looks, for those of you who have not seen this, I mean, this one would think that if it's like tossing a coin at each prime, and it will be like around half a chance that it will be pretty random whether the square, right, as you vary the primes. And it is indeed true that it's roughly it is square for half the primes and not square for half the primes. But actually, there's a much deeper story. It's much more than that. Right? And this is this marvelous law of quadratic reciprocity. As I recount in this book, I failed to understand the law of quadratic reciprocity even after reading it for 6 months. as a kid of 15. So somehow all these ideas are very simple, maybe in retrospect, but when you learn them, you struggle with new concepts of modern learning. So all this mathematics is kind of 1980s, but it still has some depth. Okay, so as I said, deep arithmetic arises by asking for the number of solutions of this equation, see what the signs are. So I want a rule. Given a prime q, I want to just be able to look at it and tell you, without doing any computation, what the answer is, whether it's 1 or minus. Right? And the law of quadratic reciprocity gives you that. Tells you that you can. Okay? So it turns out, to give you the answer, that q is, that 5 is a square mod q precisely when q leaves a remainder of 1 or 4 when divided by 5. It's going to be, okay, it's going to be there in the next slide. Sorry. Oh. Let it be. I think the next slide says this. Okay, but maybe it says it. So basically, the quadratic reciprocity law says that the local Galois symmetry at prime q, which is just a sign, either it's 1 or minus 1, it will be denoted by the symbol 5 upon q, right? Which is going to be 1 if minus is 5 is a square mod q, it's going to be minus 1 if 5 is not a square mod q. So somehow this thing which might seem random, which I would have assumed that there's no rhyme or reason, there's no pattern to this, right? But Legendre, kind of, maybe Euler, so they discovered patterns just by computation, right? Or they found these amazing patterns that actually it's a much more ordered process than you would think. And the answer is precisely that it is the square precisely when, so it's called reciprocity because 5 is a square mod q precisely when q is a square mod 5. Q being a square mod 5 is a very easy thing. Somehow it's called a reciprocity law because you kind of turn the hourglass. So 5 upon q turns again 2 upon 5. But the basic observation, the basic version of this law in this particular case is that 5 is a square mod q precisely when q is a square mod 5, which is the same as saying q is either 1 or 4 mod 5. Okay, so somehow this is what is called a reciprocity law. You look at a global equation, count its solution over prime q, look at the number, and somehow unexpected pattern in point counting is broadly what is called reciprocity. After Gauss's first, so this pattern was observed by Euler and Legendre, and they tried proving it. They couldn't. They tried it for decades. They tried it for long time. And then Gauss and the 19-year-old boy proved it, but 19-year-old proved it. Right? So he gave several proofs, and somehow this law of quadratic reciprocity has played a big role in the development of number theory. A lot of theorems aspire to be like quadratic reciprocity, and you want to generalize it to other polynomial equations. So somehow quadratic reciprocity does address patterns in local Galois symmetries attached to symmetries arising from quadratic equations. If you try to do higher degree equations, it's still terra incognita for a degree 6 equation. No one knows the problems. Right? So basically, still there's a lot of mathematics still there. But Sayre's conjecture is in the tradition of this quadratic equation, some sort of unexpected pattern. And somehow this has something to do. Okay, I'm not going to because I'm running out of time. This has something to do with roots of unity, right? So somehow the fact that the way Gauss, one of his proofs, he gave many proofs. Right? One of his proofs was his first proof was by induction and primes, which will come to. But then later on in life, he got many proofs, and one of them was using the theory of roots of unity. So the zeta 5 is just e raised to power of 2 pi I over 5. Right? So somehow you can write root 5 in terms of roots of unity, fifth roots of unity, and somehow that gives you a handle on determining these local Galois. Now again, I'm not going to really expand on this. It does take some time to understand this, but I'll just give you a hint that it's related to roots of unity. Right? Quadratic reciprocity is related to roots of unity, which we are going to see are related to some kind of reciprocity. Okay, I'm going to skip all these slides. So somehow a massive generalization of this story of quadratic reciprocity was answered by people like Kronecker and Weber and so on at the end of the 19th century, where they said that somehow they can understand symmetries of all polynomial equations defined over the rationals as long as the symmetries are abelian. In the sense, it doesn't matter in which order you do the symmetry. Anyway, sorry, some technical terms. If you don't understand it, it's fine. Right? So this is the story of the development of what is called class field theory. And one of the crowning achievements of number theory in the 20th century, the first half of the 20th century, was what is called Artin reciprocity law, which understood solution, which understood in a broader context of equations defined not just over rational numbers. It understood symmetries, it understood the local Galois symmetries, a systematic law for them, arising from polynomial equations whose Galois symmetries are kind of not so complicated. So this was a big development. More than 100 years it took to go from Gauss's quadratic reciprocity law to Artin's reciprocity law. And somehow Artin's reciprocity law gives us structural understanding of QRT. Because mathematics is, one of the themes of mathematics is this long conversation which takes place across centuries. And earlier mathematics stimulates later mathematics, and the earlier mathematics is re-understood or contextualized after newer development. Right? So mathematics, one of the great, it's a very conservative subject in the sense once proved, things remain proved. There are no like modifications of what was proved. It continues to exist forever, but it's not dead. Right? It keeps on talking to mathematics across it. All right. So this is Galois symmetry. This is Emil Artin, of course, in this German mathematician. Okay. So now what happened for the? Okay, I'm going to give you some very broad strokes. So what happened to explain Ramanujan's congruences was that people Serre and then Delisle kind of their lecture and Delisle attached these two-dimensional. So now abelian is like somehow to do with GL1. It is somehow the theory, as Andre said somewhere, it is the complex analytic theory of the exponential function. Right? So it's kind of a very easy function in complex analysis, but to understand its number theory too is the end of the 19th century. But now to understand higher reciprocity laws and to understand symmetries which are not abelian of GL2 type, people had to resort to modular forms. So Galois symmetries provided of GL2 type, so in the sense they have symmetries of roots of polynomial equations, so that the symmetries have some GL2 nature to them. They turned out to explain Ramanujan's congruences modular 2, 3, 5, 7, 20, 6, 9. So I'm not going to tell you to this. Okay. So I've already said all this, that some of this continuous development in mathematics from reciprocity to Serre's. Okay, so basically now let me end to 6:15. Yes. So Serre's conjecture seeks to understand Galois symmetries of polynomial equations somehow which have a GL2 flavor. So somehow it's a converse because Serre had conjecture and various people, Shimura, Delisle, knew how to go from a Ramanujan symmetry to a Galois symmetry in this two-dimensional kind of case, GL2 case. Serre's conjecture is a converse to that. How to go from a Galois symmetry to a Ramanujan symmetry. Right, so somehow, of course, for a lay reader, especially for the reader of my book, these symmetries, it's not clear what these symmetries are, why are they different. But somehow it's a miracle that these two symmetries, which have origins in totally different fields of mathematics, turn out to really be the same. Right? And the miraculousness, for example, is illustrated by me just telling you that somehow Serre and Fry and various people observed that if you could prove this, you got Fermat's last theorem as a consequence. Right? And that's what stimulated Wiles to prove work on Fermat's last theorem. That is the fact that it is now a consequence of a conjecture which has some structural meaning. It's not some random question. Fermat and Wiles, as a 10-year-old boy, had this dream of working on Fermat after he saw the statement in a library, the public library in Cambridge. But then he actually started working on it seriously once it was shown to be a consequence of something more structured. Okay, so this is Serre. I was going to turn 100 this year. Yes, and he's a very great mathematician of the 20th century. His work across topology, algebraic geometry, number theory, group theory. Okay, so now, let me just I'm going to resort to prose now rather than symbols. So Serre's conjecture is astonishing and Galois symmetries are discrete in some ways because they kind of come from algebra and kind of just permuting, finite many things. While Ramanujan symmetries are continuous. And the miracle of Serre's conjecture is that you're kind of intertwining, you're showing, relating discrete to continuous. That's how it's like an astonishing conjecture. I mean, of course, it is made in some context, it's many conjectures of this type, but in this particular case, this is Serre's conjecture. And first Serre, let me give you a brief history of this conjecture. He first made this conjecture in a letter to his friend John Tate in 1973. And then somehow he formulated this conjecture. Serre is a big mathematician. People, because he made this conjecture, started thinking seriously about it. Though it was fantasy when he proved this conjecture, when he stated this conjecture. There was no way to prove it. There was no way you couldn't start with it. But people still kept working it. And they developed, mathematics developed continuously in the 1970s and 80s and 90s, and all those developments we used in a solution. So some of them were very, very fact that he made this conjecture, which seemed impossible in the beginning even to think about or try to prove. In the end, led to its invention. Because Sam made the conjecture, because it excited people, because they thought about it hard, somehow that really led to. And somehow, okay, here's an interesting story. The Tate immediately proved this conjecture in one particular case. This was mod 2 Galois symmetries in level 1. And he proved it by using arguments which you will see in a first year course in graph and algebra, graph first year, graph first year. And that proof relies on the miracle, the two numbers that was 2 to the 5.2 to the 5 by 2. It relies on this numerical fact. And once you go beyond p equal to 2, some of this fact, the corresponding inequality you would want to hold doesn't hold. Especially for p. So it's somehow by some accident or by some lucky inequality, Tate could prove by a beautiful proof, elementary proof, it could prove Say's conjecture in a particular case. And it turns out that Tate's result in this case turns out to be a starting point of our work. And we leverage this because our proof, as I'll tell you, is inductive. It inducts on the prime, like Gauss's first proof of quadratic reciprocity, is an induction of primes. And this is the starting point. Okay, now again, I don't want to stress this too much. I mean, somehow, this non-existence. I mean, they proved that some of those Galois symmetries which Sayre was talking about did not exist for certain small primes. And the non-existence results of this sort were key to our work. Okay, so now let me resort to some prose now. So here I'm quoting directly from this book. So Sayre's conjecture is an organizing metaphor, right? In mathematics, it's very important to have metaphors, things that you have some organizing principles, they're showing the two different things. Okay. An equation is sometimes the most beautiful if the two sides of the equation are totally different. Somehow they're miraculously equal. So Sayre's conjecture is like a beautiful metaphor, I'm quoting from my book, which brings together two very different concepts, Galois symmetries and Ramanujan symmetries. To make an analogy with physics, one could think of the two symmetries as similar in a way to electricity and magnetism. In the 19th century, Maxwell proposes equations that tie electricity and magnetism together, making them two aspects of the electromagnetic field. This gave rise to a new physics that emphasized fields rather than mechanical forces. In an analogous way, Sayre's conjecture unifies Galois and Ramanujan symmetries, and just as electromagnetic stuff has applications within mathematics, Sayre's conjecture has powerful applications. It gives a proof of a older conjecture of Shimura and Tanya Heinweg, called the elliptic. I call it the elliptic symmetry conjecture for this book, and Fermat's theorem is also a concept. Right, so somehow, I mean, because somehow power of a conjecture or a problem is that it should solve problems which pre-existed. Right? It should solve problems which were unknown. Right? So for Sayre's conjecture does solve many earlier problems. Okay, so now, so we proved this conjecture in the period 2004 to 2009. And there's a more general conjecture, okay, instead of looking at modular from the level 1, on SL to Z, you can look at modular from the higher level called N. Okay, the Sayre's conjecture takes place in that level. Again. So Sayre's conjecture is more precise form, not only conflates two very different types of symmetries, but it asserts that some subtle properties of this symmetry, which is this number N you can attach to the level, the weight K, and I make this analogy of charge and spin of particles, which are very different. Somehow this conjecture conflates these two numbers for these two symmetries. Again, there's no a priori reason why this should be. Somehow, again, this is the miracle of mathematics. Somehow there's immense structure which is not obvious in the first symmetry. Okay, so Sayre made all these very precise conjectures, and somehow the precision of his conjecture led to a proof of it. Right? Because someone asks a very precise question, it's very helpful because somehow you know what you're aiming for. So the precision of Sayre's conjecture was really important in its proof. So the last third of this book has three parts. One when I was undergraduate, second when I was a graduate and a young researcher in Tata Institute. The third part is when we actually proved the conjecture. Right? So the last three chapters, which are called Breaking Through in Strasbourg, the level 1 case, and the oddest prime of them all. Because our proof had something to do with p equal to 2, which is the only odd prime. So the last three chapters are about this kind of exciting period in my life when we actually proved the conjecture and struggled with it and kind of all the drama, and we almost made a mistake at the end of the thing. So again, this is my French collaborator who unfortunately passed away untimely. So okay, so I'm not going to tell you this slide. Somehow there's a connection between Fermat and Sayre. Right, so somehow if you start with the counterexample to Fermat's equation for the prime p, a to the p plus b to the p plus c to the p to the 0, or non-zero integers ABC, you kind of directly go from that via some construction of phi to some Galois symmetry of small weight and level, weight 2 and level 2. And Sayre's conjecture says that this symmetry comes from a Ramanujan symmetry of the same weight and level. So it's very important to know this precise form of the conjecture. And by inspection, you can show that there is no Ramanujan symmetry of weight 2 and level. Right, so somehow the strategy of Wiles is a bit like Galois. The way Galois showed that equations don't have solutions with radicals was he produced an obstruction. He produced some of the Galois symmetry forbids the existence of solutions as radicals. So similarly here, a counterexample to Fermat's last theorem leads to a forbidden Galois symmetry, except you cannot prove it's forbidden just working with Galois symmetry. To stay purely in the realm of algebra and geometry, or algebra, is cut. You have to convert it into a Ramanujan symmetry, which is the power of Say's conjecture. Then it's obvious. Then the Ramanujan symmetry of weight 2 and level 2 does not exist. Very easy. So, the Galois symmetry is impossible. It's possible to do it without going to Ramanujan symmetry. Right, so somehow that's the power of Say's conjecture. It's like in a book, it's like converting water into wine, and it's kind of an amazing kind of prediction. It's a miraculous act. What Wiles also did, he proved Fermat via the strategy. So he converted, in this particular case, he converted a Galois symmetry into a Ramanujan symmetry. That's what we do in general for the general form of Say's conjecture. Okay, somehow Ramanujan's delta function played a key role in our work because that's one of the first cases of the conjecture we proved, and we were very happy with it because this was the first time we actually showed it. Earlier we proved some non-existence results in the style of Tate using our method. But this was the first time when there actually existed a Galois symmetry of that weight and level, weight 12 and level 1, and we could show it came as predicted by Say from the unique Ramanujan symmetry of weight 12 and level 1, which is the Ramanujan delta. That's somehow Ramanujan's work. This function. So, okay, one of the very interesting parts of our proof is about induction on primes. Right? There are very few proofs in mathematics with induction on primes. Well, primes are they're pretty unruly and math, they don't really follow a very regular pattern. It's very hard to induct on primes. But our proof does induct on primes. As you know, for induction you need somewhere to start. And the starting point is given by Tate and Say. Tate is it. Tate proves Say's conjecture from a particular case. Level 1, 2. And we use that to induct. And we leverage that into all other things. So there is almost no successful argument in maths which uses induction on primes. Right? Because the magic of the techniques we use within this incompatible system made the primes cooperative with each other enough they can induct around the process. And okay, so let me quote another passage of the book. I gave a talk on the progress towards the proof of Say's conjecture at the IAS in Princeton, focusing on my proof of the level 1 case. I walked back for the tea after the seminar with the Prof in Princeton, Peter Sarnak, who I was in the Institute Colloquium a couple of years ago. He was excited by the talk. Sarnak was excited by the talk, and he told me that the proofs in mathematics that use induction and prime numbers are exceedingly rare. The one case we could think of was Gauss's first proof of quadratic reciprocity that used such an induction. In fact, Sarnak did not tell me that, I was just telling you this now. At that time, he told me that there are no proofs using induction, but somehow it's good to twist the story a little bit. Because in some ways, so Say's conjecture was in the lineage of quadratic reciprocity, and thus this is a pure coincidence, but it was a nice coincidence that Gauss's first proof of his reciprocity law and our proof of Say's conjecture both result in induction. Right, and there's a genetic kind of Say's conjecture is a descendant of QRL, so it's kind of nice. Strategic in life. Okay, and now the last chapter in this book is called The Oddest Prime of Them All, Prime 2. In the end, we actually made a mistake. We thought we were done. We sent the paper to a journal, and the referee pointed out lemma 4.8. We cannot understand. It turned out to be wrong. Okay, so we fixed the proof, and we were very fortunate that we had such a careful referee because otherwise it would have been embarrassing to publish a flawed proof. But it took us 6-7 months to fix the proof because it was rather subtle to fix it. The proof had survived, albeit with more work, demanding an emergency injection of new and delicate ideas to deal with this case. Our faltering in the final ascent in the attack of the proof of the conjecture added an element of drama to the climax. My wife Rajni was a steadying presence through the travails of trying to fix our mistake. My daughter Arushi provided her some distraction. Our mistake at the end was like the cramps a runner might experience near the end of the race. Because we kind of struggled with this conviction for 5 years, even after we had the initial race. We were kind of tired and in haste to get to the prize. We tripped up. But in the end, it was a happy ending because we could fix the proof after months of effort. That's it. Thank you. Of course, the fundamental technique in our proof is Wiles. as I said, when Wiles first announced his work, he said his methods were orthogonal to self-conjecture. Because logically, Wiles needs a statement of self-conjecture to actually start. I mean, in particular cases of self-conjecture were known so that he could actually use them. So in some ways, it's logically seemed circular to try and use Wiles to prove self-conjecture. But it turned out that his techniques were fundamental. So we had to find a strategy which could draw upon Wiles' method, and then we had to generalize Wiles' method so that they were enough. They were good enough to justify a strategy. That's what took us. But when we found the strategy in 2004, in some ways before that there was no strategy for self-conjecture. I mean, it always seemed plausible. There was no route to. So our thrilling thing which happened in fall of 2004 is that we found a route. It seemed impossible to prove the full case. We thought it would take 5 years, 10 years, 20 years. But it seemed at that point it was within the realm of the possible. But
yeah, so there is tea outside, but before we go there, I'd like to say 2 things. One is, of course, I have to thank a couple of people here. So Professor Manjunath, Professor Ankur Kulkarni, these people have been instrumental in getting this colloquium. So Professor Manjunath is unfortunately not with us because of some work that he has. And Professor Ankur is, he's here. Okay, hi. So yeah, Professor Manjunath is here, is back here. Yeah, good to see you. Yeah. Oh, okay. So thank you as well. Yeah. So thanks to Professor Manjunath. Yeah. You weren't there for the first one. Okay. So and the Institute Colloquium Committee as well. I would like to thank them. And that's the first thing. The second thing is so which I'd like to give to our speaker. In fact, thanks to our speaker as well. Fantastic talk.